This is a demonstration of spontaneously flowing wavefronts of transition. It is supplemental to a journey through computation. It is implemented in Berkeley Snap. The demonstration consists of a ring of 30 oscillation networks linked through all of behaviors. This is the behavior network that the demonstration is emulating. These are the oscillation networks that are linked through all of behaviors that correspond to these oscillation networks, and the big red dots correspond to the all of behaviors. Now each oscillation network consists of a flow path and a closure path. And in the middle of the closure path is a conversion or an inversion, which corresponds to the middle of the flow path in the demonstration where red transitions into blue and blue transitions into red. Now the olive behavior, which corresponds to the big red dot, will transition its output to red when all of its inputs are red, will transition its output to blue when all of its inputs are blue, and if the inputs are different, it will not transition its output. The demonstration is started by clicking the red stop sign several times to clear the state of the interpreter, and then by clicking the green flag to start the interpreter. And the ring is instantiated, and then a blue wavefront is flowed through the ring to fill the ring with blue bubbles. And then a red wavefront entered by a blue wavefront is entered into the ring. And there are 3 delays in the ring, and we'll look at this delay first. And there's the red wavefront waiting on the delay. And there's the blue wavefront waiting on the delay. And now the wavefronts are separated, and here's the red wavefront flowing through blue bubbles, trailing red bubbles, and here's the blue wavefront flowing through the red bubbles, trailing blue bubbles. More about bubbles and wavefronts a bit later. Now let's look at this delay. There's the red wavefront waiting on the delay. And now there's the blue wavefront waiting on the delay. Now the slider varies the delay, right? The delays vary with the slider. Okay, so let's look at this delay. There's the red wavefront waiting. Now this delay is 4 times longer than mid and left. Now at 50, the full range is 100. So at 50, it's twice as long as these, and at 25, it's the same as these. So now we'll let that delay go, and now we have blue wavefront flowing through red bubbles, followed directly by a red wavefront trailing red bubbles. Okay, so now let's put this delay on again, and we'll reverse that again. You notice we started out with a red wavefront flowing through blue bubbles, followed by a blue wavefront trailing blue bubbles. So now we'll reverse that, because this delay is long enough for a wavefront to flow all the way around the ring. There goes the blue wavefront. So that'll flow all the way around the ring before the red wavefront gets through the delay. Okay? Okay, so now we'll release this delay. And now we have a red wavefront flowing, followed directly by a blue wavefront again. Okay, so now we can add wavefront pairs up here. You'll notice that the wavefronts have been flowing in pairs, a red wavefront followed by a blue wavefront. So now we can add wavefront pairs up here. So when we tap the space bar, it will insert a red-blue wavefront pair. Now there's a black line here, and this line represents an arbiter. And there's an arbiter here because there can be a conflict between the flowing wavefront and the entering wavefront. And we'll show this conflict here in a minute. So there's the flowing wavefront. So now the entering wavefront was delayed until the flowing wavefront got past the arbiter. So the arbiter only allows one wavefront pair to flow through it at a time. And now we'll show the let's see, when the next wavefront comes around, we'll show the insert winning the race. Okay, so now the flowing wavefront had to wait for the insert to get through the arbiter. Okay, so now we have 4 wavefront pairs in the ring, and we'll add one more. So now we have 5 wavefront pairs flowing through the ring. To take a little closer look at wavefronts and bubbles, we'll set the long delay here. And you can see the wavefronts backing up, waiting to go through the delay, and you can see the red bubbles backing up here, waiting for the blue wavefront to go into the flow into them, which is waiting at the delay. And when a wavefront flows through the delay, you can see the wavefront flowing, but you can also see a bubble flowing back through the waiting wavefronts. Okay, and we'll go one more cycle. We'll watch this one more time. There's the bubble flowing. And then we will capture a flowing bubble with the pause button here. Okay. An oscillation network can contain a red wavefront, a blue wavefront, a red bubble, or a blue bubble. And what it contains is determined by its input olive behavior. If the output of the olive behavior is blue and the closure input of the olive behavior is blue, the oscillation network contains a blue wavefront. If the output of the olive behavior is red and the closure input to the olive behavior is red, then the oscillation network contains a red wavefront. If the output of the olive behavior is blue here and the closure input is red, then the oscillation network contains a blue bubble. If the output of the olive behavior is red and the closure input is blue, then the oscillation network contains a red bubble. Each oscillation network cycles between red wavefront, red bubble, blue wavefront, blue bubble, red wavefront, red bubble, blue wavefront, blue bubble, and so on. And as each oscillation network cycles, bubbles and wavefronts flow through the ring. Now conversely, as bubbles and wavefronts flow through the ring, each oscillation network cycles between red wavefront, red bubble, blue wavefront, blue bubble, and so on. So there is no causality here. One might call it something more like collaborative consequence. There is a collaborative protocol in play here, facilitated by the olive behavior and the alternating red and blue wavefronts. And the protocol is that red wavefronts only flow into blue bubbles, and blue wavefronts only flow into red bubbles. Red wavefronts never flow into blue wavefronts. Blue wavefronts never flow into red wavefronts. Blue wavefronts never meet because they're separated by a red wavefront, and red wavefronts never meet because they are separated by a blue wavefront. At the delay, a wavefront waits to pass through the delay, and a bubble waits for a wavefront to flow into it. So here's the blue wavefront waiting at the delay, and when it gets through the delay, it will flow into this red bubble, and the blue closure will flow and become red, and this will become a blue bubble, into which this red wavefront will flow. The closure will become red-blue, and this will become a red bubble into which this blue wavefront will flow, and so on. So if we look at the bubble we caught in flight up here, this is a blue wavefront, and it's just beginning to flow into a red bubble. Right, so the blue closure is flowing here. So this gets here, will become red. So this will become red-blue. So this will become a blue bubble into which this red wavefront will flow. This will become red-blue, and this will become a red bubble into which this blue wavefront will flow. And this will become blue-red, and this will become a blue bubble into which this red wavefront will flow. And so on. So that's how bubbles flow around wavefronts, right? They flow through the closure network, around the wavefronts. So now let's look at the wavefront flow, the wavefront that fell through the delay. So we're looking at a red wavefront flowing through blue bubbles here. And this is the red wavefront. This is red, red. This is a red wavefront. This is still red, red. This is a red wavefront. Now this is red, blue, and this is a red bubble. Now this red wavefront is propagating into here, and the closure has become red and then now blue, and this blue, this is about to become blue, right? So this is about to become a red bubble. Okay, so as the red wavefront flows through the blue bubbles, it trails red bubbles, which are stretching back to the delay, waiting for a blue wavefront to flow through them. Wavefronts flow clockwise through the wavefront flow network, which I'm outlining here. And as mentioned before, bubbles flow counterclockwise through the closure network or the bubble network. Now, these two networks can be viewed as independent behavior networks that intersect through all of behaviors. So contemplate that for a while. Counterflowing, intersecting networks. When the wavefronts and bubbles start flowing again, you'll notice that the wavefronts are easy to notice because each wavefront maintains its color as it flows around a simple network, whereas the bubbles, as they flow through a somewhat more complicated network, change their color identity each time they flow. So the bubble starting here flowing through the waiting wavefronts was a red bubble, then it was a blue bubble, then it was a red bubble, then it was a blue bubble. So it's hard to notice the two flows, but both flows are occurring. Wavefronts are flowing forward into bubbles, and bubbles are flowing backwards around wavefronts. We'll get the simulation going again here. And you can see the bubble flowing through the wavefronts, waiting wavefronts, and the wavefront flowing through the waiting bubbles. Okay, we'll go one more cycle here, and then we'll release the delay. As soon as the blue wavefront falls through, we'll release the delay. All right. So we'll define the throughput of the wavefront as the number of wavefront pairs that flow past a point on the ring in 1 unit time. And we'll define the unit time as the time it takes a wavefront pair to flow completely around the ring. And we'll follow this lead wavefront around the ring. And the time it takes one wavefront pair to flow around the ring is the latency of the ring. So when we get back here, 5 wavefront pairs will have flowed through here. So the throughput of the ring is 5 wavefront pairs per latency. Now, when we had 4 wavefront pairs in the ring, it was 4 wavefront pairs per latency. And when we had 3, it was 3. When we had 2, it was 2. And when we had 1, it was 1. And each time we added a wavefront pair, the throughput of the ring increased. And that is because the latency of the ring remained constant, right? So these wavefronts are flowing around the ring just as fast as the first wavefront pair flowed around the ring. The reason for that is that there are plenty of bubbles for the wavefronts to flow into. Now there are 5 wavefront pairs, which are 5 blue wavefronts and 5 red wavefronts, which is 10 wavefronts in the ring of 30 oscillation networks, which leaves room for 20 bubbles. So there are plenty of bubbles for the wavefronts to flow into. The wavefronts aren't waiting on anything, they're free flowing around the ring. And here you notice there's a bunch of bubbles waiting on wavefronts to flow through them. Okay, let's add 2 more wavefront pairs to the ring. There's 1, 2. Now there are 7 wavefront pairs in the ring. That makes 14 wavefronts in the ring, leaving space for 16 bubbles. So there's still plenty of bubbles for the wavefronts to flow into. So the wavefronts are flowing around the ring just as fast as they have been flowing, and the latency of the ring is still the same. So now with 7 wavefront pairs in the ring, the throughput of the ring is 7 wavefront pairs per latency. Now the thing to notice here is that nobody is waiting on anything. And if we look at an olive behavior here, we'll see that the closure comes to the olive behavior almost simultaneously with the wavefront flow. And what that means is that this oscillation network becomes a bubble just as the wavefront arrives looking for a bubble to flow into. And that's what's happening all the way around the ring. If we look at one down here, we see the closure arrives just in time for the wavefront to flow through it. Okay, let's add 4 more wavefront pairs to the ring. 1, 2, 3, 4. So now there are 11 wavefront pairs in the ring, 22 wavefronts, leaving room for 8 bubbles. So there are no longer enough bubbles for all the wavefronts to flow into, but there are plenty of wavefronts for the bubbles to flow around. So a lot of wavefronts will be waiting on bubbles, and here you see a bunch of wavefronts stacked up waiting on bubbles. And here you see the bubbles free flowing through the waiting wavefronts, right? So these are the bubbles free flowing. So let's look at throughput, and we'll look at this oscillation network here once the bubbles get around. Okay, so this is a wavefront waiting on bubbles. Here come the bubbles. So there's 1 wavefront pair passed, 2 wavefront pairs passed, 3 wavefront pairs passed, 4 wavefront pairs passed, and a wavefront is waiting in this oscillation network. And here come the bubbles again. So then there's 1 wavefront pairs passed, 2 wavefront pairs passed, 3 wavefront pairs passed, 4 wavefront pairs passed, and the wavefront is waiting again. And so for every time the bubbles flow around the ring, 4 wavefront pairs pass through an oscillation network. So the latency now is how long it takes the bubbles to flow around the ring, rather than previously the latency was how long it took a wavefront to flow around the ring. Now it's how long it takes a bubble to flow around the ring. So the throughput here is 4 wavefront pairs per bubble latency. We started with 1 wavefront pair in the ring, and as we added wavefront pairs to the ring, the throughput of the ring increased. This is called wavefront limited behavior because the number of wavefronts in the ring determines the throughput, and bubbles are waiting on wavefronts. When we got to 7 wavefront pairs in the ring, the number of wavefronts in the ring and the number of bubbles in the ring were comparable, and nobody was waiting on anybody. This is called balanced behavior. Everything was occurring just in time. Nobody was waiting on anybody. As we added more wavefront pairs to the ring, the number of bubbles in the ring decreased, and the number of bubbles in the ring started determining the throughput of the ring. And wavefronts started waiting on bubbles. Now this is called bubble limited behavior. And we just saw that with the 8 bubbles determining the 4 wavefront pair throughput of the ring. And as we add more wavefront pairs, the throughput will go down. The bubble count will decrease and the throughput will go down. So let's add 3 more wavefront pairs. 1, 2, 2. Have to wait for the bubble to come by here. 3. And as each wavefront flows into the ring, a bubble flows out of the ring. And so this bubble, a wavefront flowed in and this bubble disappeared. So now we have 2 bubbles flowing around the ring, and the throughput of the ring is 1 wavefront pair per bubble latency. So we'll separate these a little bit more so you can see them flowing individually. And you can see that there are 2 bubbles flowing around the ring counterclockwise, and the throughput of the ring is 1 wavefront pair per bubble latency. The red wavefront passed, now there's a blue wavefront waiting, and the blue wavefront passed. So 1 wavefront pair passed through this oscillation network as the bubbles float around the ring. Now, if we add 1 more wavefront pair into the ring, there won't be any bubbles left. So let's do that. Now you saw up here that the wavefront was waiting at the arbiter, and the inserted wavefront didn't get in. Now the inserted wavefront will get in, and when this bubble comes around, the blue wavefront will get in. Now we have 30 wavefronts in the ring, 15 wavefront pairs, and there's no bubbles in the ring, and the ring is deadlocked. There's no recovery from deadlock in this demonstration, and we just have to start over. So we'll click the stop sign a few times, and then the green flag. Now there's another behavior mode for the ring, which is delay limited behavior, which adds another dimension of subtlety to the behavior of the ring. But that's a topic for another time. You've been watching wavefronts of transition spontaneously flowing through a network of dependency relations, negotiating pop-up delays, traffic jams, and even the external intrusion of added wavefront pairs. Now, it might look like there's some control mechanism involved, perhaps even a conscious intelligence driving each wavefront. But that is not the case. The ring network is a minimal expression of dependency relations that exhibits spontaneous and autonomous behavior, proceeding solely on its innate expressional merits. Now, it can be more complex. Each oscillation network can contain a computation behavior, such as adders and conditionals and so forth. And the flowing wavefront pair can represent data. And ring networks can be coupled and linked into complex computational networks that behave exactly like the demonstration network you've been watching. And such a network of coupled rings, realizing a deterministic computation, however, contains nothing that you familiarly associate with computation. There's no Boolean logic, there's no sequence control, or any other form of explicit control. There is no stable sampleable state, and there is no orienting common reference, such as a clock or a mathematician. Instructions to interactively access the demonstration can be found at carlfant.net. Hope this has been useful.